And the TSNE is a little bit more resource consuming, but I don't know why or in which circumstances one would be preferable over the other.
Okay, good. So we'll cover that right now. First, multiple testing issues and their correction. Well, first, what is multiple testing problem? Well, this problem arises when multiple hypotheses are tested simultaneously, and then you have a number of false positives increases as you test more number of hypotheses. So here are some ways that you can correct and you can use to deal with these problems. So you have the Bonferroni correction. This says that the corrected significance level for all tests combined is alpha divided by m. And m here is the number of hypothesis tests that you performed. And you can reject the null hypothesis when your p-value is less than the corrected significance level, which is alpha divided by m. Or if you reorganize this equation, it would be m multiplied by p-value less or equal to alpha. The second correction method to deal with multiple testing is Hom-Bonferroni. And this is a way for you to sort your p-value in increasing order. So it's like p of 1 to like p of m. And then you use this corrected significance level for the ith test, which is like whatever order it is. So alpha divided by m minus I. So whatever the position of the order of your value is, and plus 1. So then you can take that as a value to reject your null hypothesis at. So p of I is less or equal to alpha divided by m minus 1 plus 1. Or it's also reorganized as m minus I plus 1 times p of I, the p-value at the order I, less than or equal to alpha. The next method is Benjamini-Hochberg correction. So here again, you also sort your p-values in increasing orders, and you have p at 1. You have to order the same thing as Hom-Bonferroni, and then you have p of 1 to p of m. And then this corrected significance level for the ith test is going to be alpha times the order I divided by m, which means that you will reject your null hypothesis at p of I less or equal to alpha times I divided by m. And you can reorganize that at m times p of I divided by I less or equal to alpha. So you also have why do we need dimensionality reduction? Well, this is a process to reduce the number of dimensions in the feature space. So when you start to do machine learning, you can see that you can add many features to get more accurate results. And you'll start to see this, like some of the projects I've worked on, we start getting like 75 to 100 features. And a lot of them were dummy variables from categorical variables. So after a certain point, the performance and robustness of your models starts decreasing, and the computational complexity increases as you increase the number of features. So not always that more features means better. So this is a curse of dimensionality, where the sample density decreases exponentially with the increase of dimensionality. So it kind of almost looks like this curve here, where if your sample is too cluttered with too many features, it actually increases the dimensions significantly more. So we use dimensionality reduction to transform your data into low densities while keeping most of the information intact. It also helps you visualize the high dimensional data in 2D and 3D. And which leads us to PCA and TSNE, which we use for dimensionality reduction. So what is PCA and TSNE? Well, PCA stands for Principal Component Analysis. This is a dimensionality reduction technique where you can use it to identify smaller number of uncorrelated variables known as principal components from a larger data set. And the technique is widely used to emphasize variation and capture strong patterns in the data set. And you have this graph right here. You can see these two arrows. And so this is a scatter plot, and overall you can see that there's like a upward trend, right? There's some correlation here between these two variables. And you can break down those components into like essentially x and y axis, where you have your first principal component going one direction and the other one in the perpendicular direction as your second principal component. TSNE stands for Distributed Stochastic Neighbor Embedding. And this is a technique for dimensionality reduction that is particularly well suited for visualization of high-dimensional data sets. So you have TSNE labeling these clusters into its own colors here. And because this has so many different dimensions, you can see it separating it out pretty well into its all individual groups. So what's the difference between PCA and TSNE? Well, PCA tried to capture the linear structure in the data, whereas TSNE captures the nonlinear structure. PCA focus on preserving the global structure of the data, whereas TSNE focus on preserving the local structure, as in like the clusters of the data. PCA, there's no hyperparameters involved, whereas TSNE, there are some, like perplexity, number of dimensions, etc. For PCA, you work by separating the point as far as possible based on the highest variance. So you can almost think it like line of best fit, but divided into its dimensions. Whereas TSNE is more like working to group the points as close as possible based on the characteristics of these points. And PCA, and similar to line of best fit, is very easily affected by outliers, whereas TSNE, with its clustering method, will not. So let's look at a case study now. And before we do that, let me ask you, why do we use graph and networks? Anyone wants to take a chance to answer why do we study graphs and network?
Insights about so networks have these nodes and edges. So which nodes are important, which the edges can be various type of edges. So we can define a lot of things about the structure we are analyzing.
Okay, good. And what is an adjacency matrix, and how do we interpret it?
Yeah, the adjacency matrix is the matrix that represent the network. So the network represented in form of a matrix, and it contains all the points of the network, and the values inside the matrix are the edges.
Okay, good. Anyone wants to add to that?
Yeah, also if the value inside the matrix is 0, it means that the points corresponding to that edge are not linked with an edge. If the value is 1, it means that they are linked. And also depending of the edges, on if the edges are of different types, so the edges can be various types in some cases. The values can be even more than 0 or 1. Can be not binary as well.
Okay, good. Anyone else want to add to that? Nope. Okay. So let's go through the case studies right now. And I'm going to show you this one case study where we will cover air pollution data. And the context here is that, well, air pollution is all around us. And in cities and countrysides, it affects us without even realizing or not. So the rise of permissible concentrations of various pollutants observed over the last few decades contributes to rising population level, and as a result, affecting the weather conditions in a favorable manner and formation of smog phenomenon. So in fact, the affected air quality level in atmosphere has a negative impact on individual health and may cause an economic imbalance. So diseases caused by rising population levels are one of the major issues confronting urban settlements. So in this case study, we'll explore and visualize the air pollution data sets, which contains information about air molecules and pollutants found in the air. So the objective here is to reduce the number of features by using dimensionality reduction techniques like PCA and TSNE to extract insights about the data. So we have this data set that is about 13 months of data on major pollutants and the meteorological levels of a city. And the data shows average readings for nitric oxide, nitrogen dioxide, oxides of nitrogen, ozone, particulate matter like PM10 and PM2.5, sulfur dioxide, benzene, toluene, piacylene, measured in micrograms per cubic meter of air. This also shows generic features: wind speed, vertical wind speed, bar pressure, weather temp, and wind direction. As PD and previous day in data sets, we have 5 columns that are previous state values of corresponding columns in the data set. So they are PD, PM10, PD, NO2, SO2, CO, and PM2.5. And we also have date. So now that we have the overview of the data, let's import it and take a look at our data set. So we have, we can import pandas, NumPy, of course, then matplotlib, seaborn, and we can also use this method to scale the data using z-score. So that's sklearn, pre-processing, import, standard scaler, and then we import PCA and TSNE from the sklearn decomposition and manifold. Now I will load the data in. So data air pollution is equal to PV read CSV air pollution. And then let's look at the head. So here we can see we have the dates and all of the metrics of air pollution or air quality in that particular day. So now let's check for the info using the function info here. And we can observe that there's 403 observations and 27 columns in the data. And all of these columns except date and weather are numeric data type. And weather is an object data type, and so we can use dummy variables for each category and convert it to numeric data type. And the majority of the columns have missing value. And as a reminder, can someone tell me what is dummy variables and why do we do it for a categorical data type?
So dummy variables are normally used because the methods for dimensionality reduction doesn't handle well categorical variables. So that's why we use them. But I'm not sure.
Any other guesses? No other guesses? Okay. So when we mostly do models, it's all in numerical values, right? It's all numbers. But categorical variables are like, okay, like here are 3 types of flowers, blue, red, and yellow. And there's no way for a computer to understand string value, right? Which is object type data. So we can encode it with 1 and 0s, which represents essentially yes and no, and that's dummy variables. So we now from one category variable, we will create 3 additional dummy variables, which essentially tries to answer the exact same thing as that one categorical variable. So we'll create 3 new columns. Let's say flower type 1, flower type, well, let's be more specific. Flower type red, flower type yellow, flower type blue. And if it's red, then only the column red will have a 1 and the rest is 0. And we do that for the rest of the data, essentially converting it into dummy variables so that now all of your variables are numeric and your model can interpret it. It can get pretty hairy when we have too many category variables, and that's where we need to start using PCA, because let's say if you have a categorical variable that has 10 different types, now you have additional 10 different columns. That doesn't really sound great, right? Because of computational complexity. So the other thing we notice from our data is that we have missing values, and let's check the number of missing value in each column. Using this function here is null, which checks for whether or not it is null, and then the sum of that. So we get this. So we do see that we have missing value, except for just the serial number and the date. So we'll impute, which essentially means filling in these missing values. And we can use mode for categorical variables. median for skewed numerical variables, and mean for non-skewed numeric variable. And if you're wondering why, it's because of normal distribution. So let's now look at data preprocessing and exploratory data analysis. So first, let's drop the columns where it's all unique, which is serial number and date. So we'll use the drop function, and within the parameters, we'll identify the columns as this list here and in place true. For further details of how these parameters work, you can go on Python and read more of it in details. Now let's look at summary statistics. I'll use the function describe on my data frame and use .t to essentially build a table that looks like this. It just formats it into a table. So from looking at this here, what can you tell me about this data on a very preliminary level?
It seems that some variables could have outliers.
Okay. What else? I would say that, okay, normal level of PM10 is about 100 micrograms per cubic meter, and PM2 for PM2.5 level, it is about 60 micrograms per cubic meter. Here we can infer that PM10 has a high median of 250 and PM2.5 has a median of 108, which are pretty harmful to the environment and people. The higher the level of different types of particulate matter indicates that the data might belong to an urban or industrial area, and concentration of nitrogen oxide in the air should be in the range of 60 to 80 microgram per meter squared. But the mean of nitrogen oxide here is 74.4. So it is in the range that is less impact. But the standard deviation is quite high for NO, NOx, PM10, and PM2.5, which means that it varies pretty much a lot in a year because the data is around 13 months. So the maximum value of many feature reaches an alarmingly high level, indicating that there might be outliers in the data. So let's check the distribution and outliers of our numerical data now so that we can make a better judgment of how we can fill in these null values. So first, I'm just going to create a new data frame where it just only includes the numerical value of my data frame. So I can use the function select data type, include only numbers, and apply to my DF. And then I'm going to call this as a continuous columns as a list of my result data frame. Now that it's a list, I can essentially run it through in a for loop to print out all of the distribution. So for all the column in the continuous columns, I want to print the column, the skewness calculated in this skew function for that particular column, set up this figure frame, and build more subplot where each of those subplots will include a histogram with this particular size, have a Y label, and then on the subplot, the next positioning, which is what you see here is from 1 to 1. Now it's going to be 1 to 2, which is the second box of this first subplot row. We'll plot the box plot in here. And finally, we need to show it. So here's what it looks like. So I'll let you take a look, and then you can tell me what's the overall distribution between different metrics in our data. Here is our NO, CO, NO2, O3, SO2, PM 2.5, benzene, toluene, P-xylene, NOx, PM10, wind direction, NH3, RH, temperature, wind speed, vertical wind speed, solar, power pressure, PDM 2.5, PM10, NO2, SO2, CO. So overall, what do you think?
Some variables are very skewed to the left, right?
Well, if it's pointing the pointy tail to the right, then it's right skewed.
Okay, the right skewed.
A lot of the data also, or a lot of the variables have outliers.
Okay, good. What else do you notice? I would say that some are also less skewed. And go back to those. These are less skewed. And then some have pretty like kind of almost very normal distribution, but have a lot of outliers on the side. So now that we know the distribution overall, let's check the correlation using correlation matrix. So build our figure, and we implement the heat map in here, where it takes our data frame, do the correlation function, and give annotation and formatting, and show our graph, which essentially looks like this here. So from this, what can you name me just like 3 things that stands out to you in this matrix here? It is a lot, but just pick 3 things.
The levels of toluene and the wind speed are very correlated. Actually, it's a negative correlation rate.
Mm-hmm. Okay.
There's a high correlation between benzene and toluene.
Okay. Anything else? One more item.
There's like a box of highly correlated variables between the PM is particles per million, is that what it is? 2.5 through the NOx, so maybe the source of those variables is the same, like the source of the pollution.
Mm-hmm.
Very good.
Mm-hmm. Awesome. All right, so those are great points, and so let's just summarize what you see here. There's high positive correlation between these guys, right? This makes sense. Nitric oxide and their PD is respectively highly correlated. And here's some interesting part, which is negative correlation. We can see that temperature and nitric oxide are opposing forces. Vertical wind speed and sulfate, vertical wind speed and PM 2.5, wind direction and vertical wind speed. This kind of makes sense. And sulfate and wind speed again. So sulfate and wind speed are kind of negatively or correlated to each other. So here, nitrate and the fine particulate matter, 2.5, are positively correlated with their day values, like PD NO2 and PD PM 2.5, which makes sense. And then particulate matter of 2.5 micrometers in diameters, positively correlated with particulate matter of 10 micrograms in diameter. Temperature and nitrate are negatively correlated because nitric molecules in the air increases as temperature increases. And since wind speed and vertical speeds are negatively correlated to pollutants like sulfate and PM 2.5, it's because higher wind speeds generally translate to greater dispersions of air particles and resulting in lower air pollution concentration in an area with stronger wind. So now let's do some data pre-processing. We kind of now understand the data and how it's grouped, some similar thing. So let's impute missing values with mode for weather column and with median for all other columns, as majority of variables are skewed. So for column in data air pollution columns, if columns equal to weather, then we can take that column, fill the null value, fill NA, with the mode of that particular column, which is exactly what we do here with this code, and in place is true. Else, we can essentially fill the NA with the median. Right, so we are only filling the mode area with weather because mode is the categorical variable here. So next we need to create our dummy variables for our categorical variable, which is weather. So we have this function from PD called getDummies. Just need to plug in our data frame and use drop first. So that automatically does that. Next step is to scale our data. Can someone remind me as to why we need to scale our data?
I think it's because we need a common way to measure the distance.
Okay.
It's not the distance from but we need a comparability between all of our variables. So if you start from a point 0 and scale or move left or right from there, it's comparable versus trying to do it on different scales, which it would not be comparable.
Mm-hmm. Okay, thank you. Yeah, so we can define scalar as the standard scalar function. We import it in, and then we'll create a new data frame called scaled, and then we'll do a scalar fit transform on our data. Now with that, we'll just convert it back to a data frame, and then we'll take the same columns as the previous columns. Now that we have the scaled data, we can now apply PCA and TSNE that we learned about. So first step of principal component analysis is to define the number of principal components to generate. First, we need to learn what the shape of our data is. And shape at index 1 is essentially looking at how many features there are, how many columns there are. So finding the principal components for the data, we have PC1 is equal to PCA, where the n components is the number of columns, and random state equals 1. And now we rebuild it into a data frame and do a PCA1 fit. So this function that we just created, and do a fit transform on our scaled data. And since we have like a lot of components, because now we have a dummy variable, we have to do our scaling and PCA. So the percentage variance explained by each principal component is defined as exponential variance is equal to PCA1, apply the function explained variance ratio, and that will give me the percentage of variance. So next, I want to be able to visualize the explained variance by individual components. And here, do you all understand what explained variance of each individual components mean? If not, let's go back to our slides. And if you remember, we have the two component piece, and it's two arrows that point into two different dimensions. And that's kind of essentially what we are doing here. So these components that you see, we're trying to measure the variance from each of those principal components. So let's visualize this properly so we have a better understanding. So they take each of the points, take its variance from the principal component, so essentially these arrows on the graph, and then we plot it out on this graph. So plot PCA1 explained variance ratio with the cumulative sum function and with the proper encoding here. Put in a title, X and Y label, and show it. So from this here, how would you interpret this? How do you interpret this variance by components?
When you add more variables in the sample, you preserve a higher percentage of the information of the original sample, but this relation is in a decreasing growth. So maybe using 20 components, it's not very different to use 25 components, for example.
Okay.
In terms of information that contains the sample.
Okay. Anyone else want to take a stab at this?
Excuse me, can you repeat your question?
How do you interpret this data?
This graph?
Yeah.
Yeah, this is the graph that represents how the total variance evolves using more and more principal components. So you see that the first principal component is the one with the most variance, and going further and further, the principal component add less and less value to the model, even though they add some weight. And by weight, I mean they make the dataset more heavy. So you want to find the right compromise between a low number of principal components and a high value of variance. So you can use this graph to decide how many principal components you want in your analysis, depending on what your goal is.
Okay, good. So next, let's find the least number of components that can explain more than 70% of the variance. So let's put sum as 0, and for Ix and enumerate of exponential variance, we'll encode it as sum is going to be equal to sum plus I, so the next one. And this will give us the cumulative sum. So if sum is greater than 0.7, then we'll finally end the loop, and we'll print the number of PCs, principal components, that explain at least 70% of the variance as Ix plus 1 and break. So the number is 5, and we can kind of see this as well. You can see 1, 2, 3, 4, 5, and this is at the 0.7 threshold. With that, now we can make a new data frame with the first 5 principal components as columns and the original features as indices. So columns equal to a list of 5 PCs, where PC1 is going to be my data frame with the rounded components as a table from 0 to 5, and columns, and taking all the other features. The index is the scaled columns, the data frame columns, and the name as the columns. So we have this graph here. Can you tell me how would you interpret this, and what does this graph here shows, what it means, and why is it important to show this?
This matrix.
Sorry?
You're talking about this matrix.
Yeah, this matrix, this table here.
Yeah, this matrix shows how for each principal component, how each principal component is determined. So how the different variables of the original data set impact the principal component. So which component is an indicator of which variables, and if it is a strong indicator, a positive indicator or a negative one, or maybe it's not affected at all by some variables.
Good, thank you. Anyone wants to add to that?
Yeah. These correlations could help to rename the principal components. For example, if the first principal component is correlated with benzene and toluene, etc., the principal component number 1 could be renamed in order to avoid that this turning as, for example, hydrocarbons.
Good. Thank you. So overall, here's the observations from this matrix here that we can interpret. The first PCA, PC1, seems to be correlated with hydrocarbon, like benzene, toluene, xylene. And these are typically known to generate due to fuel combustion. Second principal component is related to humidity, and we can see that it also correlates with ozone layer, rain, so anything rainy season. So when humidity goes down, ozone levels goes up, which means more sunshine and more humidity, is an indication of rain and potential washaway and atmospheric pollution. Third PC, PC3, seems to be capturing air pressure because we are looking at how low pressure accompanies wind and rainy conditions, dispersing the pollution away, and higher pressure still the wind allowing pollution to build up in urban area. The fourth PC seems to be associated with high with toxic gases like SO2, and this means that it is also related to weather. The fifth PC seems to be explaining the direction of the wind as it impacts the air pollution irrespective of the concentration of all pollutants, and if the wind is blowing towards the urban area from an industrial area, then pollution are likely to be higher in the town or city than if air is blowing from another direction, for example, open farmland. So next, let's do TSNE, because we essentially broken down our data into 5 principal components here, and each kind of explain one aspect of data and how that measures air pollution. To visualize the data in the different complexity values, let's do TSNE. So I'll build a for loop for I in range from 10 to 50 at 5 intervals. And TSNE here will be defined as TSNE where the number of components is 2, random state is 1, and complexity is at whatever I it is. And data air pollution TSNE is going to be TSNE fit transform into our scaled data. Then we build a data frame. We call the column as S1 and S2, then build a figure and scatter plot, and also then name it accordingly. So this is what we have here at each different perplexity: 10, 15, 20, 25, 30, 35, 40, 45. So from these graphs here, first I need you to tell me why did we build these TSNE graph by different perplexity levels, and what does it show me, and why is it important to show this?
Excuse me, can you go over this introduction once again? I didn't really get it.
Which introduction?
The TSNE is new.
Okay, so we are essentially trying to visualize the data for the different perplexity value. So let's review here. Again, TSNE is a dimensionality reduction method to visualize high dimensional data, right? We have a lot of variables here, like a lot of variables, and we have like a dummy variable from weather as well.
So TSNE is only used for dimensional reduction, but only for 2-dimensional and 3-dimension reductions. Yeah?
Yeah.
You can, it makes no sense to do a TSNE for a 4-dimension, like from a 10-dimension dimensions data set to a 4 dimensions. It only makes sense to do it to 2-dimension or a 3-dimension to visualize it. Otherwise, it makes no sense. Am I right?
Sorta. But yes, in this case, we are looking at only 2-dimension here.
Something that confuses me about the TSNE is it looks like a grouping algorithm or grouping method, but it's not. It's dimensionality reduction. So what confuses me is that what would be the use of TSNE other than visualization? for me, the PCA made sense when you, especially when you mentioned reducing the dimension for calculations and all that. But TSNE, since you're messing a little bit more with the information you have, and you are basically grouping what's close to one thing to the other thing. I'm struggling a little bit to see why we use TSNE. What's the application?
Mm-hmm. Yeah. So before I explain that, does anyone want to take a try at answering those questions?
I don't know all the reasons, but I guess if you know that your data has a lot of outliers, TSNE, we know, is a method that handles outliers, whereas PCA is more affected by them.
Yeah. Thank you. Yeah, so like what Heather says, first, we need to understand it's just a way to visualize high dimensionality data. Like what you guys are thinking about is clustering algorithm. And we're not doing that here. We're not clustering anything. We're not building anything to memorize the way we cluster data. This just converts similarities of data points to joint probabilities and tries them to minimize the divergence between the joint probabilities of the low dimensional embedding and high dimensional data. So just a way for you to visualize the data and also to reduce the dimensions so that you can do other machine learning techniques on top of this later. So this is actually a better reduction technique than PCA for very dense data. It reduces the number of dimensions reasonably when your number of features is very high. Like let's say you have 80 features because you have a bunch of dummy variables from one categorical variable. So this will suppress some of the noise and speed up the computational thing that you need to do of the pairwise distances between these samples. And some of the functions here that we use, the parameters in that, like what is perplexity here? Perplexity is the number of nearest neighbors used in other manifold learning algorithms. So the larger the data set requires larger perplexity. So in this case we use 50, but you can choose a value between 5 to 50, and different values can result in significantly different results. So perplexity must be less than the number of the samples. You can also have like learning rates, early exaggeration in the parameters, number of iterations for the optimization, number of iterations of progress, so on and so forth. So I recommend looking on the sklearn documentation so that you can understand it a bit better. But regardless, in summary, do not confuse this for clustering algorithm. It is a statistical method to visualize high dimensional data by giving each data point a location in a 2D or 3D map. Does that make sense?
Yeah, thank you very much. So I have two follow-up questions. And back to Andrea's question, so it doesn't make sense. So if we're talking, basically what I understood from what you're saying is that it's for us to visualize the data that could be in like n-dimensional data in 2 or 3 dimensions. So would that make any sense to use PCA or TSNE to reduce a sample to 4 dimensions or to 5 dimensions in any circumstance? Or we are always going to use PCA and TSNE to reduce to less than 3 dimensions?
I think it's dependent on you and how you want the data to look. These are just tools for you to play around with. what's most common I've seen is just 2 and 3. Maybe there are cases that you need more dimensions. I'm not too sure. But regardless, it's a non-linear dimensionality reduction technique where you want to take embedding high dimensional data, but you want to visualize it in a low dimensional space of 2 to 3 dimensions. So the goal here is to get it to 2 to 3D point in such a way that similar objects are modeled by nearby points and dissimilar objects are modeled by distant points with high probability. So you can think of it in a way that TSNE constructs a probability distribution over pairs of high dimensional objects, so that similar objects are assigned high probability together, while dissimilar points have lower probability. So second, TSNE defines similar probability over the points in low dimensional map, so that you can plot them together in similar locations in the map. The original algorithm of this is using Euclidean distance, and I'm sure you've learned this in high school at least. And it essentially, Euclidean distance is calculating the distance between the objects in the base with its similarity metric. And this is kind of like a build on that. So let's not think too hard into the theories. We'll explain how it works, and maybe that will give you
excuse
more.
me.
Yeah.
So dimension is 2 or 3, is generally 2-dimension or 3-dimensions in TSNE. And I'm not really sure why perplexity is important. Can you say it more? I know you already said it, but I didn't get why is it so relevant.
Okay. So before I answer that, does anyone want to take that question as to why perplexity is important? Well, first, let's define what perplexity in TSNE is. It's a second feature of TSNE, and you can actually tune perplexity because we have seen how we kind of look at this data and how it separates into different perplexity level, right? It loosely says how to balance the attention between the local and global aspects of your data. And the parameter is like a guess about the number of close neighbors each point has. So perplexity has a very different value, different value of perplexity gives you complex effect on resulting pictures. So it kind of is a way for you to see how each point is in which cluster. So when you have a much denser data, you need higher perplexity value. And the recommended is 5 to 50. And in this case, we use a range from 5 to 50 to kind of see which one looks best and fits best into our data.
All right. So, but how can I see if the data is dense or not? Depending on the dimension of the units, of the statistical units. The more statistical units, the higher perplexity.
Yeah.
Okay, thank you. And what is it? A high number of statistical units, just to have, I guess, how many rows have we got in the pollution dataset that you use 50 perplexity?
Let's check again how much we have here. Don't remember it on the top of my head, but you can look at it in the info data. So we have 403 rows, and we have 27 columns. So we have not that much data, to be honest, but we do have a lot of variables, so it does quite add up. In real work, I have worked with data sets with millions of rows of data and also like 80 features. It gets really wonky. So this is a really good technique to learn, but for showing sake, we're using relatively small data set. So let's continue.
Okay, so 50 is the highest value of perplexity. You should not go over 50.
It is recommended to be 5 to 50.
Okay.
You can use
That's
higher,
cool.
but like it's not common to see. You can play around with it more. I would say stick to the recommended range.
Maybe it gets computationally too expensive.
Mm-hmm. Yeah.
Sorry, could you just repeat what's the meaning of dense data?
The what, sorry?
Dense data, you said that if you have dense data, you need higher perplexity. So I'm just, what's dense? Yes,
so,
dense.
Let's look at this graph here and we'll see what dense data means, right? Like, would you say this cluster of dots is very dense? I would say so because they're very close to each other, and it's also a lot of data in a very confined small space visually, right? Whereas this here, I wouldn't say is as dense as this cluster, and although this might be the same amount of dots on here, so this is less dense, this is very dense. So when we are trying to cluster our data, right, I want to put this data into groups, and let's say that your entire data is just this cluster, not cluster. If your entire data, when you visualize it, it's just a clump of very dense number of dots next to each other, I say this is very dense. Whereas if your entire data set looks like this, it's very dispersed out, very easy to cluster, very easy to pinpoint, then okay, this looks like this in here, then it's a lot easier to work with.
For instance, maybe to help Luis understand it better, I could say, like you can look at the distribution of the variables, and if the variance inside inside of each distribution is low, that is a dense data. If there is a high variance within all the variables, not between them, but in each distribution, that is a dense data.
Correct. That is a very good way to explain it. Thank you.
Thank you very much.
You're welcome.
All right, let's continue this so then we can cover the second part of our course as well. So I'll let you visualize perplexity at different level and kind of keep in mind how this perplexity changes the graph in which way we can visualize this. So overall, I can see that perplexity value of like 35 and 45 captured the underlying patterns of the data better than others. And I'll show you that one more time. So this is 35 and 45. Oh, sorry, 35 and 40. And then this is 45. Right? Because it's not too dense. It's proper clusters being formed, and we can see that. Whereas this is way too cluttered. And this is way too dispersed. So this shows that perplexity plays an important role in TSNE implementation. So let's visualize again that with perplexity equals to 35 as where clear groups are distant from each other and well separated. So first let's fit the TSNE with the number of components equal to 2, and we're choosing 2 dimensions here. Build this function, then do a fit transform on my data. Then I want to convert the embeddings into a data frame. So we have 2 columns, x1 and x2, and my TSNE data. Build a figure and build a scatter plot and show it. which gives me this. So what can you see on here?
Excuse me, but how are the two variables x1 and x1 and x2 generated? Like, what do they stand for? They're the components, yeah, but like, what are they indicating?
They're indicating the dimensions. We're essentially choosing 2D here to look at. And we choose x1 and x2 on a plane to visualize the clusters of the data.
Yeah, sure. But like, what do they stand for? Like,
we
they
don't know
are
yet.
supposed to indicate.
This is just a component we separate out, and then when we study it better, we will see what x1 and x2 mean. Right now, it just means dimension, just means component. One component.
Okay, so basically, you look at the graph and you see that some dots, so units are similar to each other, but you don't really know why. It doesn't really tell you why. It just tells you that they are similar.
Exactly, because this is a visualization technique. We are trying to visualize and understand our data better, break it down into small units.
So the TSNE gets useful when you are doing something else and you look at the results you have on two different units, and with TSNE you can see if those units are meant to be similar or not. So it's kind of a double check system. You can use it as a double check system.
Yeah, you can use both techniques to understand your data, and you'll see how it works. Usually we start off with two components so that we can visualize this on a 2D plane, X and Y, essentially. And we can see how this clusters fit together, and then we can understand further. So you'll see it now. You'll see it once we finish going through this as to why we did this. But typically, always start off with 2D as x1 and x2. That's the standard. But I'm not saying that these mean anything right now. So I can see that there's 4 different groups in the data, 1, 2, 3, 4, right? And we can now label these groups using the values of x1 and x2 axes that we labeled. So let's assign these 4 different groups. So define a function called grouping of x, where the first component is x at x1, and second component is x at x2. So if second component is greater than 12, and you're wondering where I get these numbers from, it's from these axes here. Right, and I'm trying to give it like certain threshold that I see visually here to separate these out into groupings. So here is above 12, it's going to be this, right? So second component above group 12 is going to be my group 1. And if second component is less than -10 and first component is greater than -10, which this is going to be group 2, and so on and so forth for group 3 and group 4. Now I want to define the new column called groups within my data frame TSNE, which I will essentially just apply the grouping function condition onto the data and essentially goes through each of my data points on here and put in the correct labeling for grouping. So now my data will have the original data, TSNE, and the grouping of which group it belongs to based on this. So now I can build a scatter plot to essentially color label it and make it look nice and pretty for me to visualize. So scatter plot where x1 and x2 is x and y axes, my data, and the hue is the groups that I labeled from my data. So now let's try to visualize the properties. So now we get to understand what these groups actually mean, right? So the properties of groups with respect to the numerical variables in my data. So I'm going to create all columns as my columns in a list, build a figure, and then for I in each of the variable in my columns, I'll build a subplot and then build a box plot of my variables and show it in terms of the group colors, the TSNE groups, and build a layout and put the proper title in. So here's now how we can interpret the data. So let's just look at the first one so that you can break it down and try to understand it. It's a lot, and we probably don't have enough time to cover this in details anymore. So I recommend to take a look at this further, but let's just take one example. So let's take NO, the variable NO, and how that shows in each of our group. And these all represents my data points and groups. So we can clearly see that group 4 has the highest NO group and group 1 has the lowest. And group 2 has a bit less, and then group 3 is the third place. And I will make a note for CO as well. I see a similar pattern where group 4 has the most as well, and group 1 has the least. For nitric oxide, group 4 has the most by median, but it actually doesn't have as much variance as group 3. And we go through each of these, make a note of what each group means for each variable and how they compare to the other groups relatively. And from all of this, I will gather my information and make a conclusion about what each group means and which characteristics by these variables does it have. And you can go through each of these graphs later, but I'm just going to summarize in the observations below here. So there are 4 groups. Each group have different characteristics. Group 1 represents hot and humid area, where there's less variability in pressure, wind speed is low. Higher humidity is an indication of rain and has potential to wash away atmospheric pollution, resulting in low level of pollutants, fine particulate matter, and hydrocarbon. Group 2 is medium humidity and temperature with low pressure and wind speed. The level of pollutants is medium, and these might be developing urban areas. So the ozone layer concentration is medium to high, resulting in comparatively higher solar radiation. And group 3 is the largest and represents low humidity and higher temperature areas, as the variability in pressure is high, wind speed is high, and if wind is blowing toward an urban area from industrial area, then pollution levels are likely to be higher in the town or city than the air blowing from another direction, for example, open farmland. And this might indicate a developed urban area with highest level of ozone pollutant, solar radiation as emitted by cars and power plants. And the last group is industrial area, because this has the highest concentration of hydrocarbons as a result of fuel combustion, and this has a lot of particulate matter and pollutants, less air variability, and low wind speed. So at the end, when for TSNE,
excuse me.
Yeah.
But why should I use TSNE over any other clustering algorithm? It looks
not
heavier and looks what?
It's not a clustering algorithm.
I know it's not a clustering algorithm, but basically the same insights it gives you are the same one of a clustering algorithm, even if it's not.
I guess it's a way to visualize, and it uses the clustering method, but it's not clustering algorithm. Clustering algorithm indicates that you are using clusters and then predict something else as clusters as well. But why you use this? Well, first, you essentially, when you look at the data, you have to admit that you learned a lot about understanding the data now that you went through this visualization techniques. Initially, you have 13 months of data with a bunch of variables and pollutants. You can't really say concretely about what this means or what this says, right? But at the end of TSNE, what you essentially did is that you built 4 different groups, and you can explain how different groups have specific traits to it that you can point out and explain to your boss.
Yeah, but what if I had to k-means clustering algorithm and I put 4 as a number of clusters? It gives me 4 clusters and the insights about all the clusters respect all the concerning all the variables. So basically it gives me the same result, but it's quicker.
Yeah, it could be. We're teaching you tools and teaching you basics of everything, right?
Okay.
Yeah, like a variety of tools is important, and it helps you build foundations later on, and you can use whatever you find is the most useful. Like, we usually teach you like a bunch of machine learning algorithm, like linear regression, whatever, but I also find in real life I mostly just use XGBoost because they are the most powerful machine learning tool.
Which one, sorry?
XGBoost.
Oh, I don't really know it.
We'll learn about it later.
Thank you.
We'll learn about the k-means as well later on. But this, again, is to visualize your data if you purely just want to understand. So next we have a Cavia case study where we want to look at network effect, and we'll also use the same thing as well. So you can download these files and you can take a look at it, but give me 1 second. We might go over time a little bit, so bear with me. So why do we study graphs and networks? Well, graphs shows their relationships, and it has nodes, which is indicated in vertices, like these dots here, and links, which is the edges, the lines, that creates these relationships. And you can use it to model and create relations and processes in physical, social, biological, and information system, which has a wide range of application. Community networks through social media, Google Maps, DNA frequencing, and search engine rankings. We also have an example is like, for example, social network, right? Like you can build a network of your friendship. Who knows that person. So you can have a bunch of friends, networks of who they belong to, and the social cliques they are part of. We also have adjacency matrix. We can represent the graph as an adjacency matrix where rows and columns and indices represent the nodes, and entries in matrix represent absence or presence of an edge between the nodes. So very simply to read this here, so for example, if you have 2, 1, 3, the adjacency matrix will be 0 at the first node, right? Like right here, 0, and then you have 1, and then it has a connection. And then the next one is like 1 is connected, but nothing else, right? It doesn't have any other connection. Same with number 3 here. So that's how you read it. So adjacency matrix is used to represent a graph into a mathematical form, which tells us whether there is any edges between all sets of the nodes, and the diagonal of this matrix will always be 0 if there are no self-loop in the network. So this is our data here, and for the appendix, you can read this more on your own time. It just essentially talks about centrality measures of how we look at degrees distribution, which is the probability that random chosen node at k number of connections, different measures for a node in a network, and then different types as to where we use it. If I have time, I'll go through this appendix. If not, you can read it on your own time. So this here, we are using this method to understand time-varying criminal network that was repeatedly disrupted by police force. So this one's kind of an interesting one for those who like forensics. And we get to see how criminal network is oriented in response to seizures of product of police forces. So we get to visualize this out. So the context here is that the Caveat project is essentially a bunch of people, criminals, arrested following investigation. And the investigation lasts 2 years, from 1994 to 1996. And we have the Montreal police and the Canadian police doing this. So they do hire a lot of data scientists too. During these 2 years, 11 wiretap warrants, valid for about 2 months each, were obtained. 11 matrices match these phrases. So this case is rather unique because unlike other investigation strategies, the mandate of the Caveat project is to seize drugs without arresting criminals. So we want to take their drugs, but we're not going to arrest anyone because we want to observe their patterns. So during this period, imports of trafficking network were hit and seized by police on 11 occasions. The arrest took place only that end of the investigations. Monetary losses for traffickers were estimated at $32 million. Some cases include no seizures and others included multiple. And here is what they represent in terms of an amount of money. This case is rather unique because unlike other investigative strategies, the mandate is to seize the drugs. So let's take a look at this. We have $32 million lost. Some of our phases had no seizures of drugs, whereas others had multiples. And this is what it looks like in terms of money. So phase 4, 1 seizure, 2.5 million. Phase 3 seizures, 1.3 million. Phase 7, 3.5 million, 360,000, 4.3 million. Next phase is 18.7, and the last one is 1.3 million. And the rest that is not shown here is essentially didn't have any seizure. So this is a great place to understand criminal network, but in response to upheaval of police forces. And we'll also see how these criminals are reacting to increasing number of distressing constraints. So let's understand more about the network we have. We have 110 players or people in this network. Players 1 to 82. We'll give them numbers. They're traffickers. 83 to 110 are non-traffickers, like financial investigators, accountants, importation businesses. But the mastermind is Daniel Serrero. He is the alleged mastermind of drug network in downtown Montreal, attempting to import marijuana to Canada from Morocco, transiting through Spain, and after the first seizure happening in phase 4, traffickers are reoriented to cocaine import from Colombia through US. So here's some of the people here. The main guy that you really need to know about is the mastermind of the network, which is N1. And then some of the other guys here are pretty important too, but they are lieutenant, investors, transporters, accountants, providers, more investors, airport contacts, so on and so forth. So we just want to understand and visualize the data here. We're not really building any algorithm, but we'll apply different network centrality measures to understand the importance of nodes and then visualize the centrality measures of this. First, we'll import the libraries, no different than before. But the main one that is new here is import network KX. and decorator and network KX utils for this. And then we also have imported all of these CSVs in different phases. So each of these CSV represent one phase at different police seizure. And this is what our data looks like. So here's the rows, and here's my criminals numbers and where they are in terms of positioning. So essentially our data shows in a form of adjacency matrix represented in the data frame. And the first column, unnamed 0, is set as the index so that the column names and indices should have the same data type. So let's look at the following here. I'm going to create a list with the different phases from phase 1 to 11. And now I want to set the first column as the index for all of the data frames. So for P in phases, I'm going to set index where P column starts at 0 and place as true. So this is phase 1. So everything here is indexed. It's not going to move. It's not going to change. So now that I have set the index, let's check for consistency in column names and indices data type. So P1 index, P1 columns, and the following here. The observation is the above output shows that the indices are integer data type and column names are, are integer data type, and the columns are object data type. So let's convert the column names into integer data type as well. So I have my list here of phases. I'll get an empty column. So column is equal to this empty list where I can store it into this here. So first for P in phases, which runs the loop for each phase, which in this case 11. And for I in P columns, so running the loop for each column of each phase, so double for loop. Then column append integer I, which append the column names to the list column, and then update the column names for each phase, and finally reinitiating the list column as an empty list. At the end, I'll have this list here. So overall, the transformations worked, and the indices as well as column names are now integer data type. So next, we want to generate the graphs now. And we have created the adjacency matrix, and let's now get graphs out of it. So from the pandas, we have the adjacency function, and we can pass the adjacency matrix for each phase as a data frame. So graphs here, let's create an empty list again, and we'll do a for loop. So for I and P in enumerate phases, I'll get the G is equal to graph plus the string at I plus 1, print the G out. So it's just essentially doing this. And then I'm going to get G as the from pandas adjacency. It's to just build the adjacency matrix and append it together and get the nodes. So here are our 11 graphs. But let's visualize that now so that we can see how this interact. And if you face an error, you can run this and update your decorator library and install the upgrade list. So that probably just means you don't have the decorator library in there. So now let's do a graph. So I'm just going to quickly build all the graphs by using a for loop. So for I and G in enumerate graphs, print. So these two is just to separate and for aesthetic sakes, and it just shows like this line cut, and then also graph for faces. And then from the function that I imported in, use that, draw the G with labels and put in the title. So all of this is adjacency matrix here is now finally interpreted into this beautiful graph that we can see. So I want you to observe carefully to how this progresses through time. So graph first starts with 15 nodes, so just 15 people and 18 edges, so 18 connections with people. Some of these guys know each other a lot, and some are just one pipeline. But the main guy is still Daniel Serrero, and I want you to follow him pretty specifically to see how he manages this. So this is where we didn't have any police seizure yet. The police kind of leave everyone alone for like 4 phases just to observe. And then you'll start seeing when police comes in, when the network is disrupted. But as you can see, when police didn't disrupt it, it grew substantially. It essentially almost doubled. Where you have 24 nodes now, 24 people, and 28 connections as compared to before. Phase 3, it expanded even more, 33 nodes and 56 edges now, pretty big. And phase 4, still growing, but a bit reorganized. But now this is where police seizure starts coming in, and you start to see a bit of a reduction in the connection. There's less edges now, which means less relationship. Next, I don't think there's any disruption, so they're reorganizing. 7, definitely police interruption, and you can see that this here is butt off now. And we have a very dense cluster over here. Again, police interruption again, but they're still trying to grow. Phase 9, phase 10, very heavy police interruption, and finally another one. So let's look at centrality measures and how that applies in this graph. So first we'll use degree centrality. So I want to store the degree centralities for each node of a graph in a dictionary. So degree centrality is stored in this empty dictionary. This is a dictionary. So for G in graphs at the degree centralization at G, put my degree centrality function in, and now let's look at my dictionary. So this is what I have at each phase and the degree centrality. And then we can also use even eigenvector betweenness and closeness centrality measures, just different types of centrality measures to see how the numbers varies a bit, but let's all try it so that we can learn all these different things and how they differ. So exact same method, but the only thing different here is that from the NX import, I'm just going to use these different functions to get what centrality measures I want. So now that we have all of that in the dictionaries, we can do the sort and then do a descending order sort to obtain the nodes that is most important. So essentially to get who's the mastermind behind it is. So let's do the sort now. Sort the degree centrality and to identify the most important nodes. So for IX in enumerated graphs, we'll do a temporary dictionary storage, and within that I'll do another for loop for W in the sorted matter. I'll take the degree centrality we measured, sort it by that, and reverse is true just means like descending order, and then we'll plop that in and print it out. So what you see here at each of the phases, here are essentially the 5 top most important nodes, and by important we mean like how well connected they are and how many people they know and how many relationships they have. And consistently, for most of them all throughout, 1, which is Daniel Serrero, stays at 1 or 2. But he's definitely always in the most important. So we generated the degree centrality based on the top 5 most important nodes in each phase, and we can go ahead and repeat the same exercise for the centrality measures. To understand the variation of nodes importance across the phases, we can figure out the nodes some nodes are more important than others, so we'll focus on analyzing these nodes. So let's take nodes that come up quite often here, which is 1, 3, and 12, to visualize across the faces, and we'll look at the betweenness and degree centrality only, so that we can understand how well connected they are. But you feel free to play around with this data later with the other centrality measures. So first, let's start with node 1, create an empty list for the node 1 degree and phases. Then I'll create a for loop for IXG in enumerate graph and node degree append we'll append the degree centrality at index 1 times 100 and then append it to my list. And essentially I get my list, and I do that for the different nodes, and I'll do it for degree centrality and betweenness centrality as well. So repeat this exact same code for number 3 and number 12. Now I want to plot it so I can see the importance of each node at each phases. So plotting the degree centrality for these guys, first build a figure first, and then plot the function that I just defined above, up here, essentially. That list I just created, and then put in X and Y labels accordingly. So what I see here is that when we first start off, node 1 is very important, has a very high degree of centrality, which means he's very well connected, and a lot of the nodes are surrounded around him. And he functions up until the police disruption. He loses power, and by each police disruption, he loses a lot of degree centrality, or also power as well. And these guys kind of stay the same. They don't really start off with a lot of power initially, but at the end, essentially loses all power here. And we are looking at that in terms of degree centrality, and if you look at it in terms of betweenness centrality, you kind of see it in the same trend as well. Very similar trend. So in conclusion, we have used network analysis to read adjacency matrix into graphs, and we can visualize graphs, centrality measures, and the importance of nodes based on the following, and plotted it. And I'll show you what the graph looks like. So here's the 3 guys that are the most important in this. And this one here is just color coding the graph that we've seen before. So we only have 3 minutes left of the chat. Of the class. Do you have any question for me?
No, not really.
It is a very interesting case study. I think I like this one the most out of all the one we show. But in real life, this is very specific to either social media companies or police task force, something that's more related to human relationships. But typically, I don't see this applied in real life a lot. At least in my profession anyways. All right, so if no one has any other question, we'll end the class here, and I'll let you enjoy the rest of your Saturday, and I'll see you all tomorrow morning.
Thank you.
Thank you, everyone. Goodbye.
Thank you.
Thanks. Bye.
All right, everyone, I'm done with my class. For those that want interactions, I'm going to have a live stream with Adalia later, and we can talk. Hello, everyone. But I'm going to go and take a nap now. Goodbye.